In this lesson, we will study Unit 2, Rock-Forming Minerals and Rocks. First, let's understand what minerals are. Minerals are defined as naturally occurring elements or compounds that form under various geological processes and possess a definite chemical composition. Approximately 3,300 mineral species have been discovered so far. Of these, over 200 are common minerals, and only about 30 are common rock-forming minerals. Minerals in nature exhibit a vibrant array of colors. The chemical compositions and physical properties of different minerals vary considerably. Various minerals possess distinct forms. Some individual forms are elongated in one direction, appearing columnar, rod-like, acicular, or fibrous. Some individual forms are elongated in two directions, appearing platy, lamellar, or scaly, and others are elongated in three directions, appearing equidimensional, granular, or cubic. Common aggregate forms include rod-like aggregates, columnar aggregates, platy aggregates, granular aggregates, oolitic aggregates, fibrous aggregates, and concretionary aggregates. With the rapid development of science and technology today, we can utilize instruments and equipment to analyze the mineral content in rocks, the chemical composition of minerals, microscopic morphology, and structural characteristics, thereby achieving the goal of mineral identification, include differential thermal analysis, X-ray diffraction, and polarizing microscopes. However, in the field, or when high-precision equipment is not available, we typically employ macroscopic identification. Macroscopic identification involves visual observation, aided by simple tools and reagents, to analyze the physical properties of minerals. Optical properties include color, luster, transparency, mechanical properties, and other properties. Properties include color, luster, transparency, and streak, while cleavage and fracture, along with hardness, belong to the mechanical properties of minerals. In addition to this, some minerals also possess special physical properties, such as magnetism, elasticity, and flexibility. The selective absorption and reflection of visible light by a mineral is the primary reason for objects to exhibit color. It is the most obvious and intuitive physical property of minerals. Based on the cause of coloration, it is divided into idiochromatic, allochromatic, and pseudochromatic. Idiochromatic color is the inherent color of the mineral itself, which is relatively fixed and holds significant diagnostic value. Allochromatic color is caused by impurities mixed into the mineral, which is not fixed, and varies with the impurities. Hence, it has no diagnostic value. Pseudochromatic color, on the other hand, is caused by certain physical optical processes and holds diagnostic value for certain minerals, such as the blue color of azurite, the red of cinnabar, and the green of malachite, are all the idiochromatic colors of minerals. Another example is a pure quartz crystal, which is colorless and transparent. However, it often becomes stained by the inclusion of various impurities, turning purple, pink, pale yellow, smoky black, and other different colors. These colors are considered allochromatic for quartz, unrelated to the inherent color of quartz itself, and thus hold no diagnostic value. Pseudochromatic color is caused by certain physical reasons within the mineral, such as fresh surfaces of bornite appear bronze red. After oxidation, it exhibits a bluish-purple hue due to light interference caused by a surface oxide film. The cleavage or fractures of transparent minerals can sometimes cause light interference, resulting in iridescent halos. If minerals contain oriented microscopic inclusions, when we rotate the mineral, it can exhibit changing colors. Streak refers to the color of the powder left by a mineral when scratched on an unglazed white porcelain plate. Streak can eliminate the interference of pseudochromatic colors and holds significant diagnostic value for dark-colored minerals, such as hematite ranges in color from reddish-brown to steel gray to iron black, but its streak is cherry red. Here, it's important to note, minerals with a hardness greater than that of the porcelain plate will not produce a streak. However, we can crush them and observe the color of the powder. For instance, chalcopyrite, native copper, pyrite, and native gold have similar colors, making them easy to confuse. However, the streak colors of these four minerals vary considerably. The streak of chalcopyrite is greenish-black. The streak of native copper is copper-red. The streak of pyrite is greenish-gray to black, while the streak of native gold remains golden-yellow. Therefore, streak color is of significant importance for identifying opaque metallic minerals. Transparency refers to the degree to which a mineral allows visible light to pass through. It is generally measured on a standard thickness of 0.03 millimeters. Minerals are classified as transparent, opaque, or translucent. If the outline and details of an object can be clearly seen through it, it is transparent, such as quartz and feldspar. Translucent, on the other hand, is intermediate between transparent and opaque, such as sphalerite and cinnabar. If objects behind it cannot be seen at all, it is opaque, such as pyrite and magnetite. Luster refers to the ability of minerals to reflect visible light. It is classified into metallic luster, submetallic luster, and nonmetallic luster. Nonmetallic luster can be further subdivided into vitreous luster, greasy luster, pearly luster, silky luster, dull or earthy luster, and adamantine luster, such as the cleavage surface of calcite reflects light like glass. The fractured surface of quartz appears as if coated with a layer of grease. The surface of muscovite shows a pearly luster, like the inside of a seashell. The surface of kaolinite is rough and lacks luster, appearing earthy and lusterless. Diamond, on the other hand, displays the luster of sunlight shining on a gemstone. When identifying minerals macroscopically, we need to use minerals of known hardness to scratch the mineral being identified. This helps determine the mineral S relative hardness. This method is the internationally recognized Mohs scale of hardness. It uses 10 common minerals as standards, divided into 10 grades from lowest to highest. When we lack standard minerals in the field, we can also use some common items for testing, such as a fingernail has a relative hardness of about 2.5 and can scratch talc and gypsum. Glass has a hardness of 5.5. A steel knife has a hardness of 6.5. These cannot scratch harder minerals like quartz or diamond. For ease of memorization, the instructor has created a mnemonic, namely talc, gypsum, calcite, fluorite, apatite, orthoclase, quartz, topaz, corundum, diamond. Have you all memorized it? In addition to hardness, cleavage and fracture are also important mechanical properties of minerals. Cleavage refers to a mineral S tendency to break along definite planes with smooth surfaces when subjected to an external force. Fracture refers to a mineral S tendency to break irregularly in any direction when struck by an external force. For a given mineral, the occurrence of cleavage and fracture often exhibit an inverse relationship. The more easily it cleaves, the less likely it is to fracture. Through this lesson, we have learned about the definition, forms, optical properties, and mechanical properties of rock-forming minerals. In the next lesson, we will learn together about other properties of rock-forming minerals.